I'm going to start outputting ELF relocatable object files to disk so that they're ready to pass to existing external linkers like LD. So I'm basically just going to go through this ELF object file format document and just output things just enough to create a program, but I won't do things like symbols and relocations until another time. So just to get the basic thing up and running, since I'll just be creating the relocatable object files, it means that the files I'm creating are for this linking view here. Basically at offset 0 on disk, we start with the ELF header. We don't need the program header table, that's optional. Then it's followed by a bunch of section data, and then that's followed here by the section header table, which points into the offsets on disk to describe what's in each section. The order of this stuff isn't actually sort of like, it's not, it doesn't have to be in this order. You could do the section header table first, or you could put some section data and then the header table, then some more section data, whatever you want. The only real requirement is that the ELF header has to be at offset 0. But I'll follow this layout just because really no matter what layout you select, you have to sort of like calculate sizes and offsets and fix things up before you can actually write everything to disk anyway. So I've already got the data types and structures, so I'll skip over this, and we'll just go straight to the ELF header. So I'm using this ELF64 structure. So we'll start by creating some types, I guess. So we've got file.go. In here, we'll basically create like elf.file. So this will be type file, which will be a struct. And we know that a file has sections. So a section is basically going to be a representation of like a section header and its data. So I'll take these section header fields and we'll just change them a little bit. So we'll keep them as they are for now. The offset is the offset on disk, so I will need that, but I won't necessarily be setting it myself. That will just be set as part of the writing. Same goes for size. Address is not needed in my case because address, if we go to like the section header table, the address is the it's basically the memory address, and that will be decided by the linker. So I'll just be setting this to 0 the whole time, so I'll just get rid of that from the structure. So we know that a file has sections, and the first thing that we need is the ELF header. So let's go back to the ELF header again. So file will have like a function called write2, and we'll take an IO writer. This could return an error. So if we set up the ELF header first, this will be ELF64_E header, and we'll just go and take all of the fields for this. Okay, so let's just fix the syntax here. Okay, so this first field is basically a 16-byte array. And we can see that the complete description appears in ELF identification on page 8. So here we've basically got the the indices for these different fields. So you can see, for example, these first ones have this byte, and then they spell out the word ELF here. So we just need to go all the way up until pad, really, because pad is just going to be zeros anyway, and then this is just the count of the array length. So let's just put these ones in here. So these first 4 are just going to be the constants that I've already got. Class is going to be 64 because it's a 64-bit object file. Data will be LSB because this is little endian, and in the PS ABI for x86-64 it explicitly says to use LSB. Version will be current, and actually there's a version down here as well which will also be current. And then OS ABI, I think I just will set this to none. I don't think I need any of these other ones here, so we'll just do none here. ABI version, let's get rid of that. Okay, so ABI version, let's just read through this quickly. If no values are specified for the OS ABI field for the ABI field by PS ABI supplement, or no version values are specified for the ABI determined by a particular value of the OS ABI byte, the value 0 shall be used for the ABI version byte indicates unspecified. So we'll just set that to 0 for now. Okay, so on to type. Let's go up to here. Type, I'm doing a relocatable file, so this will be etrel. Machine is EMX8664. Current is already the versions, that's fine. Entry can be 0 because this is the program entry point, so which where should it start execution. PH is program header and SH is section header. Since this is a relocatable object file, I don't have any program headers, so I'll set the offset for this to 0. Section header offset is just going to be however far from the beginning of the file it is until the section headers start, but I don't know that until I've got all of the sections and written them out and sort of aligned things how I want to. So we'll just keep this as a variable. At the very least, we know that it's going to be the size of the elf header, so we should basically just do this and say binary.size, and we can just take this. So it's going to start at least after the elf header, and then we'll just add on the size of the data for each section until we get to the end, which is where the section header should start. Okay, so that's machine version. Entry flags we'll just leave as 0 for now. EH size is the elf header size in bytes, so this will be binary.size elf header again. Program header entity size or entry size, I don't have any, so this will be 0. The number of program headers is also 0. The size of the section header entities or entries will be the binary size of elf64 section header. And the number of these that we've got will basically be the length of f.sections. Then we need a section header string index, which is the section header table index of the entry associated with the section name string table. So for this one, we could probably just do like section header string table.index. So I think sections will need to keep track of their own index. And this can be half like this maybe. And then what we would want to do is, once all of this information has been built up, we would say, for example, if error binary.write, we're going to write into the writer binary.little endian, and then we're going to write the elf header to begin with. So we'll write, so this was a write elf header, and we'll just wrap the error in there. Perhaps what I should do as well is just create a main now, so that we can just do some basic testing. So let's say we've got to, we'll import github.com polygon dot, what did I call this? Fin. This will be object elf, and we'll just import this. We'll import everything so we don't have to prefix things with elf all the time. So what we'll do here, and actually I'll also import CodeGen x86. So we'll have an encoder. And then what we'll do is, maybe I'll comment these ones out for now. What we'll do is we'll have a file, which we'll just call testing.o. If there was an error, then we will print the error and exit with exit code 1, defer closing the file. Then we'll basically say, we'll have like an elf file where we'll do write to. So this will be if error write to f. We'll just copy this into here. And then we will, okay, we just need the elf file. So this will be file. Okay, let's just do a run on this and see what we're missing. Okay, yeah, so we can't use int as the offset here. And we've got an undefined section header string table. Let's say that section header string table is, we'll just make it an empty section for now. Then we can use readelf with, I think it would be like aw and maybe lint on testing.o. Okay, so possibly corrupt elf header. It has a non-zero section header offset, but no section headers. Okay, so that's fine. So basically, our we're not writing out anything other than the elf header right now. So the size of this header is 64 bytes, which is fine, which means that we've also calculated the section header. Where is it? The start of the section headers is also 64 bytes because we've said that it's at least after the elf header, but we haven't actually written any yet. Then the rest of this looks fine. So this is little endian, which is what we'd expect. One is current. OS ABI is just a Unix system 5. So that's fine. This is a relocatable object file for AMD64. Version 1, this matches up with the current up here. And then the entry point address is 0 because we're not writing the actual executable here, or a shared object. Flags is 0 as well, so that's fine. Okay, so we're at least writing a file that readelf can actually interpret to some extent. Okay, so what I will need to do after writing the elf header is that we'd have to go through each of these sections. So this will be f.sections. And what we would want to do is do a write for all of the section data. So section probably needs a data byte slice. Then we would need to go over all of the section headers. So we've got shdr over, which we'll have to build up and generate. So these will be just like the actual shdr data structure that we've got. So this will be output directly. Okay. So I'll need to add data to here. And we need section headers, which I guess this will also be, okay, so to generate the section headers, I'll have to go over all of the sections. So we'll go over the sections, And the section header offset will be pushed forwards by how much data there is. So we'll do a plus equals of length of section data. And I'll need to build up section headers here. So we just want to append a section header for each of the sections that we've got. Okay. Okay, well, so we don't have any sections yet, so that makes sense. Okay, that's still just going to be outputting the elf header itself. Okay, so we've done the elf header. This is just describing little endian versus big endian. Okay, so sections. An object file section header table lets one locate all the file's sections. So it's just an array of section header structs, which we'll write out to disk. The section header entry size gives the size in bytes of each entry, so that's fine. We've already done that. If the number of sections is greater than or equal to low reserve, then we basically put some different values in by the looks of it. Special section indexes. Some section header table indexes are reserved for in contexts where the index size is restricted, which I don't think we're going to be getting to right now, so we'll skip over this. So there's a note here, which is that although index 0 is reserved for the undefined value, the section header table contains an entry for index 0. If the section header member of the elf header says a file has 6 entries in the section table, they have the indices 0 through 5. The contents of the initial entry are specified in the first section header table entry. So this is basically saying that the first section and first section header table entry is basically a null entry. It's all zeros. So I suppose we need a way to push sections into the file. So let's say we've got f file. We'll say add section. So if we do it this way, then we can just set the section's index as the length of f.sections. So that we don't have to keep track of it from the outside. And we can say that if the section, so we might, if we push on a null section ourselves, we don't want to do anything. But if the first section that we push in is not a null section, we need to add that. So we'll say that if the length of the f.sections is nothing, and the section we're pushing in has a type that is not, was it section header type null? Then we'll say f.sections equals append f.sections, where we'll just pass in an empty section ourselves. I think that will do for add section right now. So if we go to, well, let's finish this off first. So, oh, we also need to figure out what to do about the section header string table. So if a section header string table is already pushed in, we'll need to find it. Okay, let's just do this. We'll just say that for the sections range over f.sections, let's do a switch here because I think we're going to have to find other sections as well. So we'll say in the case that the section type equals section header type, I think this is string tab. Yeah, string table. And the section's name is, I think this is in special sections. So section header string tab, same as my variable name anyway, so let's just put that in there. Then in this case, we'll set this to whatever the section is. But if this was nil, then we will set it to a section that we add ourselves, where we'll say that the name, I suppose here I want name to be a string really, don't I? This should be a string. Yeah. Okay, so we'll say the name should be section header string table. What else do we need to set? This will be type, should be the section header type string table. And then I think maybe address align could be needed. So some sections have address alignment constraints. For example, if a section holds a double word, the system must ensure double word alignment for the entire section. It's currently 0 and positive integral powers of 2 are allowed. Values 0 and 1 mean the section has no alignment constraints. So maybe what I'll do here is I'll say that address align is 1 for this, because it's just a section full of strings. So this will be a string table. So string table sections hold null terminated character sequences, commonly called strings. The object file uses these strings to represent symbol and section names. One references a string as an index into the string table section. The first byte, which is index 0, is defined to hold a null character. So that's why we've got null at the beginning here. So we'll basically start and end with null. So the empty string is basically index 0, which we can see here. Yeah, so if you passed in empty, you could actually use this. Okay, and this is a section as well. So I think actually I'm going to need to keep a map of strings, which will be the map of string to the index of the byte that the string starts at. And so when we need a way to easily add strings. So we'll say section, we'll do add string. This will be string, this is just a string. And we'll return the index. So we need to make sure that the first thing is a null byte. So if s.strings has not been created yet, then we'll say that this is a map of string to elf half, which will be that the empty string maps to index 0, and the data in this case will be a byte slice where the first byte is just the null byte. Then we'll say that if we find the index in strings, then we'll just return the index. Otherwise, the index will be the length. So this is going to be half with the length of s.data. Yeah, that will be the index. We'll return the index down here. We'll want to set the strings to the index in the map, and then we'll also want to append the data. So this will be the byte slice of the string that's passed in, and we want to make sure that it's null terminated, so we'll put a 0 byte on the end there as well. So this will basically intern the strings and give us the offset into the byte slice. So it's okay for us to add the same strings over and over again. Okay, I think that makes sense. Okay, which means as well, okay, so name here is, let's see, so we've got section header string table. Which basically stores all of the string names of the sections. But I need to push all of that data into that section before I get to actually storing the headers, because I need to know what the length is for that section before I calculate the section header offset. So I think here I'll need to loop over all of the sections again. And this time we'll basically say that the string table add string, and we'll do just section name. So this will pre-populate that section with all of the section header strings for the names. Then we need to create these section headers. So name here is just the index of the name. So we can get the name from the section header string table by just saying add string again with the section's name. That gives us the index here. The type, most of these things can just be taken directly from the section. The offset cannot be taken from there. This will just be the current section header offset, I think. The size will be the, what was size? Size is X word. Okay, so the size is going to be the length of the section's data. Let's just do a run on this. So cannot use name. Oh, it's word. Okay. Okay, let's change. So add string here, this is going to be word. Which means that this needs to change to word. Okay, section address, this is undefined because we're going to just set this to 0. Okay. So somewhere in here as well, actually, it mentions, it might be somewhere around the data representation. So here it says that the object file supports various processes. Wait, is this the right part? There's some other part that mentions alignment. Yeah, okay, so all data structures that the object file defines, which I assume means like section headers and things like that, follow the natural size alignment guidelines for the relevant class. If necessary, data structures contain explicit padding to ensure 8-byte alignment for 8-byte objects, 4-byte alignment for 4-byte objects, to force structure sizes to a multiple of 4 or 8, and so forth. Data also have suitable alignment from the beginning of the file. Thus, for example, a structure containing an ELF32 adder, which will be 4 bytes, will be aligned on a 4-byte boundary within the file. Since I'm using 64-bit section headers, that means that they need to start on disk at an 8-byte aligned offset. If I'm putting all of the section headers after the section data, the data could be literally any size. So after each, after I loop over all of these, before adding to the section header offset, if I want it to start on an 8-byte alignment for the section headers, probably the easiest way to do that is to add padding to the end of each section's data to make them go up to the next 8-byte aligned offset. So in here, we just say that if padding, we'll just calculate padding as being aligned of, let's say the end of this section's data would be the current offset plus the length of the data. So we've got section header offsets plus the length of the section's data. So if we want to align the end to an 8-byte offset, the padding will be the difference of that from the end. So if padding here is greater than 0, then we'll just append a bunch of 0 bytes to data. So let's make a byte slice with padding and just spread the zeros into there. So then the section header offset will always be the next 8-byte aligned offset, I think. Okay. Let's see if I've missed anything here. That seems okay. Let's go to main now. So what we'll need to do here... Okay, I think we'll use the encoder now. So the encoder will say emits. Let's say we do like a syscall for exit or something. So this will be nil. What would it be? I think we need to mov into the first argument. I think is di. So if we mov into di, the immediate 1, 2, 3. This will be d word maybe. Then we want to mov into, should this be d-word as well? I think we want to mov into ax is where you put the index of the syscall function. So this, I think 60 is the exit. Then we want to do a syscall. So now enc.code will contain all of that code for the syscall. Then we'll want to do, for example, ef.add section. So we'll add a section where the name will be text, and the data will be the code from the encoder. And somewhere in here, I think it's special sections. If we're doing text, then we need to set the type to prog bits. And where do attributes go? Attributes go in... So we've got type. It might be flags. Let's just try this in flags. Okay, so we'll do, oh yeah, SHF, I assume, is section header flags. So flags will go into here. This is a bitwise OR. Oh, that's an init array. We need to go to this one. This will be alloc with exec instructions, bitwise OR. Then I think the address align of this should be 16. So this is like the in-memory alignment. Okay, let's just try this. Okay, I need to uncomment that. Okay, let's readelf again. Okay, so let's see, we've got... Oh, I'm not... what am I not outputting here then? So we've got number of section headers is 1. Section header string table index is out of range. Number of section headers is 1. I mean, it should be 2. This should push... Oh, yeah, I actually need to push on the section that I'm passing in. Okay, so now we've got a few sections here. So we've got the null section, which is always supposed to be at 0. So that's fine, that's got type of null. Then we've got the .text section, which is the one that I actually added. So it automatically inserted the null before my text section. Here we've got prog bits, which is fine. The offset is 40, which is the same as this one. This should probably be 0, really. So let's just fix that. Let's see, we go to write. So let's have offset can be set to the section header offset, but if I equals 0, then we'll just say that offset is 0. Okay, let's have a look at this again. So we've got offset 0, size 0, that's fine. No flags here. This one is allocate and execute for the flags for this with an alignment of 16. The string table, which is our section header string table, is index 2. So that's this index here. Can't see any warnings from the lint option here. Number of section headers is 3, which is also fine. The start of the section headers is 104, so this is obviously working because the section headers is printing out properly without any sort of like corruption or anything. Yeah, I think this is looking like it's all okay. Yeah, 104 is divisible by 8, so that means that the section headers are starting on an 8-byte boundary on disk, which is what I expect. Okay, let's just see if LD does anything with this. So this is testing.o. So we'll say LD testing.o. Okay, so it's complaining that it can't find the symbol start. That's fine because I haven't done symbols yet. So it's defaulting to this. Maybe we can read elf for a.out now. So text is being put at the address that it's just defaulting to. And entry is going to that default address as well, so it should run my code. Was there like obj dump or something? I can't remember the flags for this thing. Well, we definitely want M to be Intel. Let's see. File headers, blah, 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 blah. Okay. Do I need to provide much here? Maybe I can just say like testing.o. No, I have to actually provide something. Okay, so what do I want to see here? Disassemble. Okay, yeah, here we go. So in the text section is a mov into EDI, because I did a mov into dword of DI. 7b would be 1, 2, 3 here, because that's what I put in. Then another dword mov into EAX. I assume this must be 60 here, and then a syscall. So if we run this and then echo the return code, we get 1, 2, 3. So this is actually executing exit with the 1, 2, 3 that I put in the argument, the first argument register. So that looks like it's all working okay. Okay, so that's writing basic ELF files. I guess next I'll move on to symbols and then relocations.